Good morning, everyone. My name is David Sir, and today, Ben Calkins and I will present our thesis entitled Experimental Study of Addition of Half-rounds to a Flat-Bottom Hull for Reduction of Hull Slamming Accelerations. Before moving forward, we would like to acknowledge the following members of faculty for their contributions to this thesis. First of all, we would like to thank our advisor, Professor Royce, for his experience, guidance, and advice throughout this entire thesis project. Additionally, we would like to thank Professor Gallagher and Professor Harris for their help with the thesis document. And finally, Professor Golden for his help with the Innovation Lab facilities during construction. I will begin this presentation by discussing some of the necessary background. I will then state the objective and go over the theory behind our thesis. Furthermore, I will discuss the equipment design and construction before describing the test procedure. I will then pass the presentation off to Ben, who will discuss the results and conclusions and finish the presentation with recommendations for future work. This thesis was primarily inspired by a common problem found in the marine industry, sea keeping. Hull improvements such as axe bows, X bows, and wave piercing bows require fine hull forms with high drafts. Other solutions include mechanical shrouds or actuating surfaces. These solutions are often more complex, costly, and prone to failure. Furthermore, none of these solutions lend themselves towards use in shallow water, specifically in the application of landing craft. Landing craft have an extremely unique purpose that incurs significant limitations on their design. With their primary mission requiring the delivery of heavy equipment in shallow water all the way onto the beach, draft is a significant limiting factor. Flat-bottom hull forms offer the benefit of high displacement for heavy equipment, significant deck area capable of carrying vehicles, the easy integration of a bow door, and desirable unbeaching characteristics. In the figure, a typical landing craft body plan can be seen, exhibiting a near flat bottom with a slight angle of dead rise, meaning a vertical separation between the vessel's keel and its chine, as indicated by the arrow. This is typical of smaller workhorse landing craft, such as the Landing Craft Utility Series used worldwide. Flat and near flat bottom hulls are specifically vulnerable to a sea keeping phenomenon known as slamming. As the hull of a landing craft cannot become finer, this is a significant issue. Slamming is defined as the impact caused by a hull surface rapidly re-entering the water in a seaway. The bow of the vessel is the most likely to experience slamming as the vessel dips into wave troughs and impacts the next wave. Bow emergence, the cause of impact, is not only more likely with lower drafts, but flat surfaces such as a landing craft's hull and bow door are subject to some of the highest slamming loads. This combination creates a uniquely frequent and high-impact slamming events. These events involve near instantaneous pressure spikes, sometimes over only a few milliseconds. These impacts can cause significant discomfort for crew and passengers, with the motions inducing sickness and injury as internal organs and joints are stressed. This is particularly dangerous for soldiers on a landing craft, as they must be in good shape for potential combat. Additionally, with potential hull girder stress increases of up to 30% from normal cycles, the induced slamming vibrations and peaks can cause significant fatigue damage. The figure to the right demonstrates the potential effect of slamming on a typical hull girder stress cycle. The x-axis represents time, while the y-axis describes stress. Note the additional peaks caused by slamming impact vibration propagating throughout the hull girder. To avoid these issues, vessels are often required to modify their operating profiles to remain safe. This generally occurs through the reduction of operating speed. This causes the encounter frequency in a seaway to be reduced, and in turn reduces the likelihood of bow emergence and the resulting water impact. The figure, showing sea state on the x-axis and ship speed on the y-axis, describes the safe operating area for a vessel. The arrow indicates the sloping reduction of ship speed as sea state increases, with up to 40% reductions experienced during normal transit. Speed reduction due to waves is especially relevant for landing craft, as shallow water causes an increase in wave height, as well as the chance to encounter breaking waves. In contested environments that landing craft may find themselves in, speed is critical, and any reduction is unwelcome and dangerous. A potential solution to the slamming problem experienced by flat-bottom hulls are half-rounds. This refers to half cylinders attached to a surface experiencing a slamming load. This combines the regime of wedge and cylindrical slamming, whereas wedge models are primarily described by surface wetting and cylindrical slamming is known for the creation of water jets. The creation of these water jets during the initial impact of the half rounds can potentially throw water beyond the bounds of the wedge itself and disrupt the surface wetting. This can reduce the area over which slamming pressure is applied, which in turn reduces the force on the model and the ultimate acceleration. This phenomenon is similar to spray rails found on planing vessels. The figure demonstrates an end section of the model used for this thesis, with the half rounds decreasing in size and mounted on a bottom plate, exhibiting a 3-degree dead-rise angle. This leads us to the objective of our thesis, to investigate the effectiveness of longitudinal half rounds for reducing slamming of a low dead-rise hull by constructing a wedge model for drop testing with several bottom configurations. So why drop testing? Drop testing involves physically recreating a slamming impact using an extruded 2D section. The results of these tests are rarely used to produce scalable results, but are ideal for conducting comparative analysis on specific geometric features for impact changes. Drop testing has also been utilized to validate numerical solutions for water entry problems. However, this is not investigated during this thesis. Drop testing is often investigated using wedge models. These models are defined by two plates forming a bottom surface with a given dead-rise angle. All wedge models used in drop testing must be able to achieve 3 goals: housing the required sensors, dropping evenly and without interference, and most importantly, surviving the impact and remaining rigid throughout. An example of a wedge model for drop testing can be seen on this slide. Note the box section indicating the vessel's dead-rise angle of 20 degrees. This example, taken from Professor Royce's dissertation, shares many of its characteristics with our own. As mentioned previously, a wedge model must survive the impact and remain rigid. Its ability to do so is estimated through the investigation of hydroelasticity, or the hull flexure from impact pressure. This comes about through the lack of adequate internal structure in terms of longitudinal stiffening and transversely due to unsupported length. Hull flexure on impact can cause a significant effect on results as they are now susceptible to greater vibration. Wedge model assumptions, such as hydroelasticity, rely on the presence of non-zero dead rise. As the model used for this thesis has a dead rise of 3 degrees, it satisfies this condition. Hydroelasticity is eliminated through the application of the Falkenson number. The Falkenson number is a non-dimensional number developed specifically for wedge impact. It uses the model's dead rise angle, beta, the impact velocity, v, the flexural rigidity, d, and the unsupported length, L, and the model material density, rho. Values of R greater than 2 indicate that the model is rigid throughout the impact. After the full design of our test rig, R values above 4 were calculated at all drop heights, indicating rigidity. In addition to adhering to the Falkenson number, expected impact accelerations were also calculated to ensure that acceleration would be measurable by the selected equipment. This was accomplished using the sectional force coefficient. As seen in the figure, the sectional force coefficient on the y-axis increases exponentially as dead rise angle beta on the x-axis decreases, with the difference between single-digit angles being extremely large. The sectional force coefficient is applied with the fluid density, model breadth, and impact velocity to find an estimated force. Because the model is of set design and made to be rigid, the only variable that can be easily changed in this equation is the drop height, a component of drop velocity. Now that the force has been calculated, the expected acceleration can be found using the relationship between force and mass times acceleration. The relevant mass is the mass of the model plus the additional added mass of the displaced water upon impact. The figure to the right represents a collection of experimental and theoretical added mass coefficients graphed on the y-axis as a function of the dead rise angle beta on the x-axis. Using the added mass coefficient, waterline breadth, and dead rise angle, the actual added mass can be found. After the application of this estimation, the expected acceleration was found to fall within the measurable range for a drop height of 6 inches with a model weight of 100 pounds. In practice, the loads are measurable at all tested drop heights. As previously discussed, the analysis conducted was used several pieces of equipment. As Webb Institute has never conducted drop testing, there were no existing facilities, so much of it needed to be designed and constructed from scratch. The necessary equipment includes the wedge model, known from now on as the test cylinder, the test pool, the drop device, and the required instrumentation. The test cylinder was designed with an overall length of 4 feet, a beam of 1 foot, and a depth of an additional foot, in order to prevent deck immersion due to impact sinkage. The cylinder itself was constructed of AC radiata pine plywood. This material was readily available at local hardware stores and offered the desired strength and construction properties. The plywood was then coated with an epoxy for additional strength and waterproofing. The internal part of the cylinder is divided into 4 watertight compartments through the use of 3 half-inch transverse bulkheads with longitudinal stiffening running through the entire length of the model. Each of these compartments houses sandbags that bring the model up to its total weight of 100 pounds. The bottom plates, representing the impact surfaces, are interchangeable and constructed of the same material as the main box. The bottom plate is highlighted in red in this image. There were 4 bottom plates created for this project, representing 4 conditions. The first being the bare or naked case with a 3-degree wedge without the half rounds depicted in the image. The next condition being a base plate with a single half round, the next with 3, and the last condition having 5 half rounds. These half rounds decrease in size as they move outboard. Each half round is constructed from Schedule 40 PVC with nominal diameters of 1, 3/4, and ½ inches moving from center line out. The base plates are secured to the test cylinder through 4 screws passing through the bottom. These screws are epoxied internally within each bottom plate, and nuts are applied on the internal test cylinder side. This setup resulted in minimal leakage within each compartment and allowed for bottom conditions to be swapped quickly. As you can see in the figure, the 4 bolts align with the center of each watertight compartment along the length of the cylinder. Due to lacking designated facilities for drop testing, a number of options were investigated for the test pool, including the use of the Robinson Model Basin. After some investigation, the Robinson Model Basin was deemed unsuitable for this purpose due to the risk of splashing sensitive electronic equipment. Additionally, the depth could not be reasonably changed, and without someone in the test pool, model recovery would have been challenging. For these reasons, a new above-ground test pool constructed of a rented roll-off dumpster was selected. This pool offered the necessary strength to hold the depths of water required and could be easily waterproofed. This waterproofing was achieved by sealing the swinging door with silicone caulk and lining the internal area with a plastic paint sheet. This test pool was located outside of Haberly Laboratory, where splashing did not endanger any sensitive equipment. The drop device was constructed of 2x4s and deck screws designed to rest on the edge of the test pool. The gusset plates seen in the image provided structural strength and stability, while the central spanning beam supports the prop boat pulley and the release hook. The release mechanism was required to release the model quickly and be reset easily without causing any additional motions during the drop. The selected mechanism was a Peck and Hale release-o-matic hook model H44L. This model was more than adequate to support the test cylinder at its full weight and was constructed of stainless steel in order to preserve it for future use. The final part of the necessary equipment was the instrumentation used to measure the accelerations. The selected device was an NDAC shock and vibration sensor. This sensor housed 2 accelerometers, the first being capable of measuring up to 100 Gs of acceleration at a frequency of 20,000 Hertz. The second with the ability to measure up to 40 Gs and 4,000 Hertz. Both sensors behaved as expected, with correct gravitational values being noted during each drop test. Due to its higher reporting rate and greater limit, the 100 G accelerometer was selected as the primary recording device. The sensor itself was mounted inside a waterproof case attached to the transverse bulkhead corresponding to the quarter cord of the model. This was done to remove error due to first mode vibration. The quarter cord is a node and is thus unaffected. The tests conducted for this thesis consisted of 3 sets, each one testing a specific variable. The first set of tests involved varying the drop height. Using a naked base plate with no half rounds in a water depth of 24 inches, drop heights of 6, 9, and 12 inches were tested. The next set of tests involved varying the water depth, as shallow water slamming was of interest to this thesis. These tests were conducted with a naked base plate at a variety of drop heights. These varied drop heights were used as impact sinkage was significant at the higher drop heights, and drop height was lowered to 6 inches for the lowest depth of 15 inches to prevent hitting the bottom of the tank. To preserve the validity of this comparison, all results were compared non-dimensionally. The final set of tests compared the effects of the new base plates with different sets of half rounds. The three configurations, 1, 3, and 5 half rounds, were tested at a constant drop height of 9 inches and a water depth of 24 inches. The drop height of 9 inches was selected for comparison as it offered a good balance between clear impacts and less structural damage from the 12-inch drop height. Each test was conducted using the following procedure. Prior to any test, the first step was to clean the test pool of any debris. As the test pool was located outside, pollen and leaves would accumulate when not testing. Then, the model would be set up by attaching the desired base plate for the relevant test. The model was then attached to the quick-release hook. While suspended, the sandbag weights were then placed in each correct compartment. The accelerometer would then be activated, sealed, and mounted within the test cylinder. Then, the model was leveled and trimmed using a trimming weight and hoisted to the correct height. The support rope running through the quick-release hook was then positioned correctly in order to ensure a successful drop. The test cylinder motions were then eliminated and the model would be dropped. Following impact, the model was quickly recovered and attached to the quick-release hook to be hoisted. Steps 6 through 9 are then repeated for each additional test in that configuration. This is a video of the finalized drop test. At this point, I would like to pass the presentation to Ben Calkins, who will discuss the results and conclusions.
Thank you, David. Moving on to the results of our thesis. The first step was to complete post-processing of the raw data. The accelerometer produces data in a file format that can only be opened using NDAC Lab software. The first step in processing the data requires removing a static value from the data that has been recorded. This is because the 100G accelerometer only measures changes in acceleration. While at a constant value of acceleration, it will decay back to a value of -1 Gs. This value must be removed from the data before it can be used. To handle this process, NDAC Lab removes the average value of acceleration from the time stream. In the figure, you can see an example set of data that was recorded by the accelerometer. In the case of the figure, the average value will be around -1 Gs, resulting in correct and usable data. However, when exporting just the several milliseconds of an impact event, the mean of the impact event itself will be removed. This creates data that is not useful. For this reason, a Python program was created to complete the mean removal process ourselves. The Python script for post-processing was developed to complete the mean removal task such that the data was usable, and it was then expanded to also identify the peak acceleration for each impact event and to non-dimensionalize the data. To ensure that the data being compared is consistent throughout the results tables, non-dimensionalization of the data was performed. The non-dimensionalization attempts to remove confounding effects from the data, especially the effect of the drop height. The method of non-dimensionalization used in our thesis is the same method used by Professor Royce in his dissertation, to remain consistent with the formulas we used for predicting accelerations. The formula for non-dimensional acceleration can be seen to the left, where A represents acceleration in its dimensional form, B represents the model breadth, D represents the drop height, and G is acceleration due to gravity. The effect of this formula is chiefly to remove the effect of the drop height from the acceleration. We also non-dimensionalize time using the formula to the right. In this formula, T represents dimensional time, V is the impact velocity, and B is the model breadth. Again, this formula removes the impact of drop height because the velocity is a function of drop height. According to the findings in Professor Royce's 2001 dissertation, drop height has no impact on non-dimensional acceleration at a constant weight. To reaffirm this finding, data for drops at 3 different drop heights, 6, 9, and 12 inches, were processed. The maximum acceleration, as well as the resulting value for non-dimensional acceleration, were collected in a table. Then, the average and standard error of these values was calculated. During the processing, it was noted that some drops resulted in outliers. An example of an outlier is highlighted here. These values will be discussed further later. The averages and standard errors for each drop height were tabulated to produce the table seen here. While acceleration increases with a drop height, there is no trend present in the non-dimensional acceleration. This finding is best understood by looking at a plot of one impact event from each of the three drop heights. The plot shown here includes a drop from 6 inches, 9 inches, and 12 inches. On the y-axis, non-dimensional acceleration is plotted, and on the x-axis, we have non-dimensional time. Each impact event shows a clear increase from freefall up to the same value of non-dimensional acceleration. This reaffirms the finding by Professor Royce in 2001 and confirms the non-dimensionalization is removing the influence of drop height from our results. During the literature review for this thesis, information about the effect of the depth on slamming was not forthcoming, so a short investigation of its effects were planned. Because landing craft, the original inspiration for this thesis, often operate in shallow water, the information is relevant to our study. Data was processed for drops performed with 3 different water heights, 24, 21, and 15 inches. No trend is present in the non-dimensional acceleration for the drop height studied. Note the larger acceleration for this drop here because it was carried out at a different water height. Note a shallower depth was not tested for fear of slamming the model into the bottom of the test pool. While water depth may impact the peak acceleration at some point, it may not become a factor until the depth is so shallow that the vessel is likely to slam into the bottom of the seaway. Finally, the data for the half-round study itself was processed, including drops for all 4 bottom configurations, 0, 1, 3, and 5 half-rounds. The bottom with 1 half-round was found to experience, on average, 21% lower peak non-dimensional accelerations. Furthermore, the 3 half-round configuration experienced, on average, 24% lower peak accelerations. Finally, the 5 half-round configuration experienced 32% lower average peak accelerations. The trend of increased reduction strengthens the case that half-rounds are reducing the peak slamming acceleration. During the processing of the data, several outliers were identified and excluded from the results. The significant variance in the data warrants a discussion of potential causes. There are several reasons hypothesized to explain some of the variance between the drops, including baseplate separation, heel and trim effects, and the environment. First, the baseplate and drop cylinder were not always perfectly flush. Creating resin-covered plywood surfaces that were completely flat was incredibly difficult. Some space remained between the baseplates and the drop cylinder when they were fastened together. Additionally, as the model was used, it became wet, and then between days of testing, it dried out. This caused some warping and further separation between the baseplates and the drop cylinder. The drop cylinder with an attached baseplate is shown here. The arrow points out separation between the baseplate and the drop cylinder. Zooming in, it can be seen that there is some separation between the 2 parts. Towards the end of our testing, this gap could sometimes reach around 1/4 of an inch toward the corners of the model. You can see this effect also in the results. This plot here shows an impact event for the bare plate, with non-dimensional acceleration on the y-axis and non-dimensional time on the x-axis. In this case, the impact event recorded a shape that looks like the ideal impact event. The plot shown here is another drop of the bare plate. This time, there are 2 peaks, hypothesized to be the bottom plate slamming into the water, and then the drop cylinder slamming into the bottom plate. Despite the double peak behavior, the peak acceleration still behaves as predicted. Another likely source of variance is the effect of changing trim and heel. The model was balanced with ballast consisting of sandbags. Before a drop test, the sand was arranged to eliminate trim and heel. However, every time the model was dropped, the violence of the impact caused the sand to shift. This required the sand to be readjusted in between every drop. This is important because a small change in the heel of the model could cause a very large difference in the character of the impact event. This can be seen in the figure. The model to the right has a slight heel and is about to impact the water more like a flat plate. The model to the left is about to impact and experience the expected impact accelerations. These effects can again be investigated with plots of the impacts. The event here is a drop of the 3 half-round configuration. The peaks are hypothesized to represent the centerline half-round, outboard half-rounds, base plate, and then the model cylinder slamming into the base plate in sequence. In other cases, such as the event shown here, the sequential peaks are much more difficult to identify, likely because the model did not impact the water exactly as expected. Overall, the trim and heel are likely having an effect on the impact events and causing some of the outliers that were recorded. Finally, environmental factors are also likely present in the variance of the data. Because the testing was completed outside, wind caused the model to sway on the hook. The accelerometer has the fidelity to record the accelerations caused by the wind. Additionally, some waves were present in the test pool. While the waves from the impact events themselves could be expected to dissipate, the wind waves were constantly regenerated. The wavy surface of the water could exacerbate the effect of the model not impacting the surface exactly as expected. However, despite the sources of variance, all the studies produced clear trends and the data performed as expected. To conclude, this thesis found that water depth has no impact on peak slamming acceleration for the drop heights and water depth studied. The half-round study found that 1 half-round caused a significant reduction in the peak slamming acceleration, and additional half-rounds were found to further decrease the peak slamming acceleration. For vessels that cannot employ narrow hull forms because of draft constraints, the half-round presents an alternative way to reduce the accelerations without compromising carrying capacity of the hull. Furthermore, for vessels that are planning to beach themselves, the ability to avoid complex mechanical appendages is another bonus. Finally, in terms of the cost of an entire vessel, the added expense of welding a few pipes to the hull will be minimal. Certain vessel types could find this combination of characteristics highly desirable, particularly for military landing craft, the original inspiration of the study. The combination of high slamming reduction, minimal displacement effect, absence of delicate parts, and low construction cost may prove particularly attractive. The results presented here create several opportunities for future work. First, further investigation of half-rounds could be performed, including tests of new half-round arrangements and a study of the best diameter relative to model breadth. Additionally, other impacts could be studied, like the resistance and maneuverability effects. A study of half-rounds using an alternative slamming test procedure could also be performed, including a test with a model in the tow tank. Finally, the equipment that we have acquired for this process and the procedure we have created for this report can be used at Webb Institute for further drop tests on other designs. Thank you for attending our presentation titled An Experimental Study on Addition of Half-Rounds to a Flat Bottom Hull for Reduction of Hull Slamming Accelerations. Please hold all questions until the next presentation has concluded. I now welcome Rain Duff and Anna Lindberg to present their thesis.